today we will cover instead a quite specific topic, which is called kernel methods and regularization. This is one of the main techniques which are used in supervised learning. So it's a very important technique, and it builds on the idea of linear regression. So it's very similar to linear regression and squares, as you have seen them last week. But there are some important novelties, in particular the idea of lifting your space to a feature space. Okay, so you have, the main idea that we see today is how to generalize linear function to a linear function, maintaining a nice property of the square, so reality. I guess you all have lecture notes, or perhaps is anybody missing lecture notes? Yes. Well, I have a few more, but I didn't count so many students, so perhaps you can share. Here are a few more. You can pass them around. Who's missing lecture notes can share with his neighbor, and you will find lecture notes in the course website, which is Marcus' webpage. More next week. So this is a list of topics for today. Has anybody heard about linear region regression? One, two. Anybody has heard about kernel methods? So the material is quite new, but some of you are not completely new. So these are the list of topics I want to cover today. And so here is, again, is another view. Okay. So as I said, we show today how to extend these squares to work with linear regressions. And the central idea is the idea of feature maps and kernels. The feature map is simply a function which maps the inputs into a new space, which is called the feature space. And this way, the original method is now non-linear in the original inputs, but linear in the feature space. So this is the main idea of kernel methods. Very simple. Before going there, let's review a few things from last week. So let's review the idea of linear regression and regularization. So in machine learning and statistics, you often have to face the following problem, and this is the main problem addressed in this course. So you have a training set of sample, right, which are a list of input-outputs. Input is denoted by xi, and it's a vector, d-dimensional vector. So d is the dimension of the vector. And the yi are the outputs, and here are taken to be scalars, so real numbers. So we also study in the course the case in which the outputs are categorical variables, so for example, binary variable for binary classification. This will be the topic of next week. But today the outputs are real numbers. So The point is that if the data is generated without noise from an underlying function, which is linear, so if the output is computed as the inner product of a vector W bar with the input X, and if the number of data points denoted by M is equal to the dimension of the input space, B, so if the number of data points is equal to the number of variables, the number of variables being the number of components of the input and the parameter vectors W, then there is a unique vector which solves this linear system of equations, right? Because you have as many equations as unknowns, and if the points are in generic position, which it's always fair to assume, then there is a unique solution to this equation, which is exactly W bar, and there is no learning is needed in this case. Okay. However, this is not the typical case that we face in machine learning. So typically, the number of data points is much smaller than the dimensionality of the input space. So there are many more parameters to find from the data than equations. And also, the outputs are not computed from an underlying function, but rather are, there is an underlying function, but the outputs are computed with there is some additive noise to the outputs. Okay? So it's not reasonable to assume that the output is exactly given by a linear equation. So in this case, the problem of recover the underlying parameter vectors from the data is not well posed. So there is not a unique solution to this equation. And what do we do? So this is what we want to discuss today. So first, I recall the definition of ill-posed problems. So, a problem is ill-posed if it is not well-posed. And well-posedness means three things. So, first, a solution exists. Just think of the linear equation. A solution exists. The solution is unique to the equation. It also depends continuously on the data. So this means that if you change a little bit the data, so in this case the matrix X, and or the vector Y, then the solution changes a little bit. Depends continuously on your measurements. Now, the learning problems we study in the course, so in supervised learning and statistics, are ill-posed within this setting, mainly because of the second condition, because the solution is not unique. Okay? So the typical situation is one in which you can find a solution, but the solution is not unique because you have less data than unknowns. Okay? So regularization provides a framework for modifying the problem so that it is well posed and we can find a solution to satisfy these three points. Unique solution, the solution exists, is unique, and you can continuously solve it. And this in statistics goes under the name of rigid regression. It's the same thing. And here we will do some motivation behind rigid regression, which is in the next slide. So the idea is that in order to find a unique solution, we restrict the possible set of values of the parameter we seek. Okay? So this vector W, which we want to solve this linear equation, is not unique, but then we start to add some constraints about which values the parameter vector can take. And so one way to do that is to introduce a family of sets, or they're also called hypothesis spaces or hypothesis classes. So each of this set HR is, in this specific case of linear regression, is a subset of the dimensional space. For example, it could be a ball, right? And this class is usually a nested class. So the index R, so the larger the index R, the bigger the set, the bigger the ball, right? And as R becomes smaller, then so R could be the radius. You could take this R as the radius of the ball. So one way to try to make the problem well posed is to try to restrict the set where we solve the equations. An alternative compatible way with linear regression is to instead design, so rather than working directly with a set, with a constraint, try to modify empirical risk minimization that you have seen also last week by a penalized empirical risk minimization. And this is the approach that we will discuss today. So regression is based on this proposal. Okay. So rather than minimizing the empirical error, which is the first term, it is empirical error, right? And if the data are obtained without noise, as we discussed at the beginning, the minimum of empirical error is 0, and the solution, the minimizer, is a vector which solves the linear equation. So rather than minimize the empirical error, we minimize this regularized or penalized error, where we add this second term, which is just the sum of the square of the components of our vector, or if you like, the square Euclidean norm of the vector. Okay? And here, what is important, there is a parameter, which is fixed in this proposal, positive parameter lambda, which intuitively controls the importance of the two terms, right? The sum I want to minimize. So the larger lambda, the more important is to, the more important when we minimize this penalized error is the second term. So we will try to find a vector which has a small norm, right? Whereas if lambda is small, we will try to find a function which has a small error. But still, since there are many functions which make the error 0, among those we will find the one which has the smallest norm. But still, the norm might be quite large. Okay. Now, to appreciate fully the idea behind this method, you need to wait a little bit, and I'm not sure the course will fully give you a picture of what's going on here, but so for sure we need to wait the introduction of feature maps and so linear models. But the conclusion is that the second term can also be interpreted as a measure of smoothness of the function to try to learn. Okay. We will not discuss this in full details in this course. Advanced topics in machine learning for the next term will give more detailed and rigorous information about these ideas, but I think we will get some of the main ideas in this course. So now to move comfortably with these kind of things, you don't need to know much about mathematics, so don't be scared by all these formulas. You just need to be comfortable with vector and matrix notation, because sometimes we move from one to the other. Right? So this is what, from here, you see that the same function we minimize can be written in matrix notation this way. Right? So, capital X is a matrix which has S rows. The first row is the first data point. We also write x1 transpose, the second data point, and so on. So X is a matrix which is M times D. Okay. Remember, M is the number of data points, and this is the dimension. So then you take the derivative, you set it equal to 0. That's the way to find the minimum. Function. And you do some linear algebra, which we don't, I think we tried already last week, pretty much. And you find this equation. The solution must solve this equation. And then you arrange the terms, and you see that you can solve it. There is a unique solution to this equation, which is given by this vector W, right? It is obtained by inverting this matrix, then multiply by this vector x transpose y. Is this clear to everybody, or you have some questions? So you can interrupt anytime during the course. Just don't take phone calls, so please turn the phone off or silent. But you can interrupt any time if something is not clear. So that's the purpose of maybe. Okay, so don't be shy. Ask any question when something is not clear. Okay? So for now, our next goal is to analyze this equation before moving to kernels and feature spaces. And what we want to understand is this idea that even though here the parameter vector W is the d-dimensional vector, right? So here, for example, I need to invert this matrix, which is d times d. So I need to solve the system with the equation to find parameter vector W. However, the point that I want to highlight in the next slides, and this is the main motivation for kernel methods, is that there is an alternative way to express the vector W, which involves only m parameters. Okay? And m, as I said already many times, might be much smaller than d, so this alternative way is more convenient for us. So how we do that? Here, if you look at this equation, you can perhaps already guess that even though the vector W is d-dimensional, this equation implicitly, it's not explicitly, what it tells us is that the vector W is a linear combination of the m data points. Okay? It is not written explicitly, so it's not clear. Equation. So that's where we want to go. We need to remember, recall a little bit the notion of singular value decomposition. Who has heard about singular value decomposition? So, a minority. Don't worry, because tomorrow, for those of you who are in the program or whoever is interested, or hopefully not everybody, otherwise we have to check and find it in the room. But there is another course that I'm teaching with Mark, which is GIO7, mathematical programming, etc. Tomorrow we review singular value decomposition, linear algebra, and then singular value decomposition. So those of you who are not comfortable with these things, strongly encouraged to attend. Okay? I would say is one of the prerequisites for machine learning statistics. So it's a very important tool. But you see not only in this course, but other courses. So for example, principal component analysis is based on singular value decomposition. Right, so here is just a quick summary of what singular value decomposition is. It's you can see it as an extension of the eigenvalue decomposition, which is perhaps more widely known, to rectangular matrices. Okay? So when you have a matrix which is square and symmetric, you can write it in a compact form in terms of the eigenvector and eigenvalues. So here the idea is quite similar. So the idea is to rewrite your matrix in a compact way in terms as a product of matrices which have some simple properties. So here I write my matrix X transpose, right? Now, the reason of the transpose is not important there, it's just because I need it later. That is a bit confusing. But, so the point that X transpose is a matrix. Right? So I write it as the product of a matrix U, which is an orthogonal matrix, which means that it is square and the columns form an orthonormal vectors. This is summarized by the operation. This means that if I take every two columns of U, the inner product is 0 unless these are the same. So this is a very simple matrix. This orthogonal matrix. Then sigma, right, is instead a diagonal matrix. It is not square because U and V have different dimensions, but it's a matrix which is different from 0 only along the diagonal. And all the elements are non-negative. Okay? And V is another orthogonal matrix. So U is a basis for the column space of X, and V a basis for the row space of X. We also use the convention that the diagonal elements of sigma, which are called the singular values, are ordered in non-increasing fashion. Okay? And also an important property of this decomposition is that the number of non-zero singular values is equal to the rank of the matrix, which is at most equal to the minimum between M and D. Okay. So this is, in few words, the singular value decomposition. Now you can. Now we're going to apply this. We're going to apply these tools. Can you see clearly over there? Is it clear enough? So I can see it. So we are now going to apply singular value decomposition to the rigid regression equation. Okay? Before we do that, one last observation which follows from SPD is also called. Now, if you take these two matrices, X transpose X and X transpose, right? So these two matrices are very similar, but you just move one around the other. Right? So they're different dimensions. So X transpose X has dimension D times D, right? Right. Because remember, X is the matrix which has as many nodes as data points. So X transpose is M times M, and X transpose X is D times D. Now, these two matrices are symmetric, and they're also positive semi-definite, which means that all the eigenvalues are non-zero. And from the singular value decomposition that we have not proven, we have taken as a fact, we conclude, it should be clear to you that the singular value decomposition implies that the eigenvalues of these two matrices are the same. Right? And I've written that here in this way. So the eigenvectors are different. So they are the eigenvectors of the first matrix are the left singular vectors, U. The eigenvectors of this other matrix are the right singular vectors, V. But the eigenvalues are the same, right? So and are equal to the square of the singular values. Okay. So this is an important fact that we will use now and follow immediately from the singular value composition. Right? So, for example, equal to x transpose x, you write mu sigma v transpose, so this is v. Then x is the transpose of this matrix, so it is equal to v sigma u transpose. Right? Now this is equal to the identity, and then sigma times sigma is equal to sigma square, so just the element square, and so you get the result. So now let's use these formulas for our for ridge regression. So we have, a few slides before, we have seen that the solution of the regularized least square is given by satisfy this equation. Now, if you then use this equation here, right, and this equation here, we use them here and here, and we do some algebra, which is very much similar to what I've done here, you arrive to this formula. Well, you first arrive to this formula in matrix notation, and then when you write in vector notation, you arrive to this formula. So you see that your solution is a linear combination of the left singular vectors ui, right? So this is a vector, whereas this is a scalar, right? So what this says is that the vector w is a linear combination of the left singular vector with some coefficients, and the coefficients are, well, it should be these numbers. Right? So we also write these. So here, what is interesting is that this parameter lambda, right? So the larger it is, the smaller the coefficient. So the parameter lambda shrinks the coefficient to 0, right? And in particular, if the eigenvalues lambda I, right, are much smaller than lambda, the corresponding coefficient is negligible, right? It's very small compared to the others. Right? You can see this method as a low pass filter. Right? So again, vectors, singular vectors ui, which corresponds to small eigenvalues, have a low weight in forming the solution. And how low the weight is depends on the regularization parameter, lambda. Now in particular, it is interesting to consider the case in which lambda becomes more and smaller and goes to 0. Right? And this is an interesting case because we started this discussion from the least square property imposed, right? So when lambda is equal to 0, the solution may not be unique. However, as lambda goes to 0, so here, as we see from the discussion, for every value of lambda, the solution is unique. Right? So the matrix is invertible, and this is the solution. So for every value of lambda, the solution is unique. And what is more, these procedures also allows us to define a limiting solution as lambda goes to 0. This is what is called the generalized solution. And it is written by this formula. So it's what is called the pseudo-inverse of the matrix x times y. But the pseudo-inverse is simply obtained by, and here there is a typo, simply obtained by the singular value decomposition of x by inverting the singular value which are non-zero. Okay. So if the matrix X was square and invertible, the pseudo-inverse will just be the inverse of the matrix. But if it is not, it is a different object. Okay? Now, when lambda goes to 0, my solution goes to this vector, which is obtained by applying the pseudo-inverse of X to the vector Y. And we don't see this in detail here, but these, the generalized solution, so the limit of the regularized solution as lambda goes to 0, has a geometric interpretation. It is the vector which, among those which minimize the empirical error, also called empirical risk, has the smallest norm. In particular, if the empirical error can be made to 0, because I have less, say, equations that are known, so I can interpolate my data. Right? Among all the interpolates, this vector W0 is the one which has the smallest norm. So it has this limiting vector as this simple geometric interpretation. Any questions? Yeah.
In what case do we have n smaller than d? Because normally we have lots of data points and not so many input dimensions.
Yes, you will see this in a moment. So when we lift these to nonlinear functions, it will be the case that the number of data points is smaller than the dimension of the feature space. Yeah. Yeah. But I would say that this is frequent also in the linear case. So for example, you could have, you want to, well, for example, in the case of classification, right? You could have high definition images, which are, I don't know, 50 times 50, so you have 2,000 more dimensions, but maybe you have a few hundred data points. So it's well possible that in some practical application, the number of data points is more than dimension. So here, the underlying heuristic and intuition is that if the data points are generated by a vector which has small norm, maybe this method will work. Because here we have restricted the norm of the vector, but if the vector which generates the data happens to have small norm, our restriction kind of goes in the right direction, makes sense. So this is very much an heuristic, but it gives you some. So we now start the discussion about these dual representations and move to feature maps. So far we have seen a way to replace widely used least squares by regularizing the square, also called ridge regression, and using singular variable composition we have kind of touched a little bit the properties of the solution. We've seen how the solution depends on the parameter lambda, the resolution parameter, and in particular what happens when lambda goes to 0. And I want to discuss a different way, which I have announced before, of writing the regularized solution. And so the observation is that the regularized solution can be also be written as a linear combination of the data points. But it is much more important what we've seen so far because it will lead to feature maps. So the question is, why is this possible, and how do I determine these coefficients? Right? So my learning algorithm then will be given the data points and given the outputs, find these coefficients alpha. Well, and the answer is very simple. It's still a linear system of equations because everything was quadratic, so we need to solve the linear system of equations. But now the linear system of equations involves m coefficients, and is obtained by inverting this matrix, right, which is instead of x transpose x is x transpose plus lambda times the identity matrix. So it's a very similar equation to the previous one, but it is potentially a much smaller system equation. Okay. So the previous equation we sometimes call so when we write our function as W transpose X, it should be bold. We sometimes call this a primal form, right? Whereas this equation is called a dual form. So the equation which highlights these coefficients alpha. And here I'm using some notation that you find, for example, in the book of Christianini and Taylor, which is one of the books which are kind of following this lecture. I mentioned in the beginning. Okay. So how do we show that this is true? Actually, it's a nice little trick. We well, we need to remember equation 1, which I'm going to write here, right? So when we have taken the gradient of the regularized error and set it to 0, we obtain this equation 1, which I now rewrite a little bit more, moving the coefficient 2. We got this equation, right? And then this you can rewrite as W. W is equal to X transpose Y minus X W divided by lambda. You just make explicit what W is equal to. And then, well, this is just when you write this in vector notation. So here you have, remember, here you have a matrix. This is a matrix, a big matrix, right? And this is a vector, right? Because it's Y minus X times the vector W. This is a matrix. So this you can rewrite as the sum of the columns of the matrix X transpose times the component, the coefficients of this vector. And this is exactly this equation. So this is writes as the sum over I, so the I column of X is the I data point, so it's Xi, right? And here you have Yi minus Xi transpose W divided by lambda. So again, to understand these formulas, you need to move from matrix to vector notation comfortably. So if there is one exercise to do to understand these notes so far, you just do practice a little bit with moving from matrix to vectors. Okay. Okay. I think all you need to know is that when you take a matrix, you multiply it by a vector that is equal to the sum of the columns of the matrix times the corresponding coefficient of the vector. Is this clear to everybody? So it's a very important point. So if it's not clear, just ask and say one more time in different words. So what I'm saying is that you take a matrix A, right? And you multiply it times a vector. Let's call it Z, right?
We can't see it.
No. So this is the same as the sum over the columns of A, that we call them AI, times the corresponding element of Z, Zi. So here, AI is vector, and Zi is a coefficient, right? So here, in this equation, A, hopefully this doesn't confuse you. So A is X transpose, right? And Z is this vector Y minus XW, sorry, this equation, divided by lambda, right? Okay. But then I need to remember that the I column of X transpose is the I data point, Xi. So you need to remember what is the X and X transpose. So then if you practice a little bit with this, everything should be, so it's like speaking English. So you need to become fluent, and it took me a long time and still struggling, but hopefully mathematics is more, there are no exceptions. is either 0 or 1. Okay, so, and tomorrow we'll do some warm-ups for the analysis and so on. But I want to say this is it's really important to be comfortable with linear algebra if you want to understand the course. So then this discussion to make it clear that, so indeed, yes, we can write our vector W as a linear combination of data points, but also this discussion tells us more, right? Because now here, if we take these equations, right, and we substitute W, so we place, we use this equation into this equation. So we replace W by the right-hand side here, right, by the sum of alpha I xi. Then we obtain a linear system of equation in alpha, the vectors, the coefficient vectors alpha. And then if we do some rearrangement, then we arrive to this linear system of equation, right, which tells us that the coefficient vector alpha is obtained by inverting this times y, right? What I wrote in the previous slide. So this shows that. So this shows what we had claimed here. Okay. So we prove this equation and then. So now let's stop for a moment before the break and analyze the result that we have found. Okay. So there are some computational considerations to make, and which are expected. So as I've said already before, solving for W requires essentially order the square operation. So the time complexity order of the squares, because I have to solve in a system of the equations, and inverting the matrix takes order the cube time. Whereas solving for alpha, the complexity is essentially order of m cubed. Okay. So if m is much more than d, then the dual representation is more convenient. And this is most or all what we care about. There is another point which is important, but I would say less important, is that what about computing the function, right? Because once we have the vector W or the coefficients alpha, then we still need to compute the value of the learned function, our prediction at the new input x, right? So if we work with the primal form, we will need to compute the inner product between W and x, which takes order D operations. Whereas if we work with the dual form, when we do W transpose x, we need, rather than work directly with W, we need to compute the sum over I, and then we have alpha I, xi transpose x, right? So this will require order of m times d operation, because we need to compute d scalar products. Okay. This is kind of stupid because in this case, W is equal to d, so just sum these things up, and then you have W. But as we will now see after the break, when we go to kernel method, we cannot directly compute W. Okay, so these considerations are meaningful in this case. Okay. And now, very quickly, you can, this is just a little detour, you can speed up this computation when you have sparse representations. So when the input is, when the vector x has many of its components equal to 0, right? And this is, for example, I don't know if you have seen it last week, but it is, for example, the case when you represent documents or binary images, right? So the pixel can be either 0 or 1, black or white, and in the case of text documents, you could have little d could be 10,000 because you have 10,000 words that you monitor in your document, maybe a bit less, let's say. But if the document is short, it will be only 300 words which appear there. Or when you remove stop words, it will be even less. So when you have this little Reuters news, right? The number of words is very small, and they give you a quick information about what happened in the word. So then your representation of this object of the document is a sparse representation in which the vector x has all of its most of its components equal to 0, except 100 or 200, which where you put the frequency of that word in the document. So in this case, you have sparse representation, and then you can make this computation faster because, so for example, the inner product between two sparse vectors is not anymore order of d, but is order of k. Because you can encode efficiently a sparse representation in a list. So these things can be speed up. So I guess you want to make two breaks. You can find one break. Who is for one break? Yeah. Who is for two breaks? Go. 1.5. I think the two breaks win. But one more time. One break. Let's say 12. One.